A 5-day-old embryo survives by aggressively burrowing into maternal tissue. This anchoring process requires the blastocyst to exert active chemical and mechanical force. By the time it reaches the uterus, the embryo is running on empty. It arrives with limited cellular energy, and its survival depends on immediate attachment. To bypass the mother's natural defenses, it must execute a multi-stage siege, shattering its protective casing, dissolving maternal tissue, hijacking a blood supply, and suppressing the immune system. This complex maneuver is coordinated by a microscopic, seemingly simple cluster of cells that possesses the exact machinery required to execute the strike. Early pregnancy is a calculated struggle for biological survival, an invasion that must succeed before the embryo's energy reserves are spent. At this stage of development, the embryo is known as a blastocyst. It consists of an inner cell mass forming the fetus and an outer perimeter of specialized cells. A rigid shell with zona pellucida encases them for protection. But inside the uterus, this shell actively prevents the embryo from tethering to the wall. On approximately day 5, the embryo synthesizes enzymes to chemically dissolve a hole in this casing. It then squeezes its way out, a process known as hatching, which must occur before implantation can begin. The act of hatching transforms the blastocyst from an insulated passenger into an exposed active invader. The hatched blastocyst drifts along the endometrium, the thick, nutrient-rich lining of the maternal uterus. Implantation requires specific spatial orientation. The inner cell mass must point directly toward the uterine wall. Once aligned, outer cells of the embryo make physical contact and adhere to the maternal tissue. This outer layer, responsible for driving the connection, is the trophoblast. Friction from this contact triggers the trophoblast to begin rapid cellular division, thickening the interface between the two bodies. This initial touch activates the embryo's outer skin, turning it into an active engine for reproduction. As the trophoblast multiplies, it separates into two functional layers. The inner layer, or cytotrophoblast, maintains its individual cell boundaries to protect the embryo's core. Cells in direct contact with the mother melt away their borders, fusing to form the syncytiotrophoblast, a single, flowing, multinucleated entity designed to burrow. This expanding mass secretes high concentrations of hyaluronidase. This enzyme dissolves the proteoglycans, the protein connections holding the mother's uterine cells together. The syncytiotrophoblast weaponizes these enzymes to melt a path directly through the uterine lining, carving an opening for the embryo to sink into. Burrowing into the tissue is a means to an end. The embryo needs to secure a high-volume maternal nutrient supply. The syncytiotrophoblast reaches deep into the endometrium until it strikes maternal capillaries, breaking their walls. This creates microscopic pools of blood known as lacunae. Nutrients and oxygen from these pools diffuse directly into the embryonic mass, sustaining its rapid growth. To prevent an immune response, the embryo releases hormones like HCG. These localized immunosuppressants shield the invading tissue from white blood cells. The syncytiotrophoblast provides the essential interface between mother and child, acting simultaneously as a chemical drill, a nutrient sponge, and an immunological shield. The embryo's invasive machinery is completely blind. It has no way of detecting its actual physical location. Fertilization occurs in the fallopian tube. From there, the embryo must travel several days to reach the thick-walled uterus, where implantation is safe. The biological timer for hatching and activation cannot be delayed. If the transit is slowed by physical obstructions, the melting engine will deploy wherever the embryo is currently located. When the embryo activates inside the narrow fallopian tube, it creates an ectopic pregnancy. The very survival mechanism that ensures life in the uterus becomes a catastrophic liability when triggered in the wrong environment. Roadblocks such as salpingitis, scarring from inflammation, can trap the traveling embryo, forcing it to deploy its invasive cells prematurely. Unlike the thick uterine lining, the walls of the fallopian tube are thin and highly fragile. The syncytiotrophoblast executes its programming without error, using its enzymes to melt through the delicate wall of the fallopian tube. This unchecked invasion inevitably ruptures the tube, leading to severe internal maternal bleeding. The embryo is non-viable in this scenario, as the fallopian tube lacks the vascular architecture to sustain its development. Successful reproduction relies on a razor-thin margin of error. It requires cellular engineering of immense power, but also flawless timing and geographical alignment to ensure that power is unleashed only where the body can handle it.